Okay, so this question is about projectile motion. So over here a body is thrown from the surface of the earth at an angle alpha to the horizontal with initial velocity v naught, assuming the air drag to be negligible. Okay, find the first part is the time of motion, second part is the maximum height of ascent and horizontal range at, and there are basically several parts relating to the displacements, the height, the time, etc. of the projectile. Still, let's read from here. At what value of the angle alpha they will be equal to each other, the maximum height of ascent and horizontal range, when they be equal to each other. The equation of the trajectory y in terms of x, we have seen some problems before in which y was given in terms of t and x was given in terms of t. It's very simple to calculate y of x after that. So basically the equation of trajectory where y and x are displacements along vertical and the horizontal respectively, and the curvature radii of trajectory at its initial point and at its peak. Okay. Let's start. So if we go for the first part, first of all the setup is, let's say this is the initial throwing point, right, A. Let's say the particle is thrown at A and it is at an angle, thrown at an angle alpha. To the horizontal. Okay. Now one thing, we'll assume that in let's say it is being thrown like, so basically the direction in which it is being thrown, I mean if it is thrown towards, let's say, I mean towards the right direction, let's consider this as right and this as left for now. Okay, so it is being thrown towards the right direction, so we'll consider this as the positive x and vertical as the positive y. Okay, so this was for anyways for explanation, so I just remove this. All right, so basically it is thrown at an angle alpha to the horizontal with initial velocity v naught. The initial velocity is v naught. The trajectory shape will be something like this. Yeah, so basically the time of motion is, so since it is thrown from the surface of the earth, right, it is thrown from the surface, so basically let's say this is the surface. Okay, right, so when it hits the surface again, so this is at t equal to 0, of course, this is at t equal to 0, right, and this is at t equal to capital T, where capital T is the time of motion. So first we need to find that capital T. Okay, fine. Now one thing, since it is coming back to the same height again, it is basically symmetrical, right? So basically the velocity with which the angle at which it was basically projected, it will come back in the same angle. So basically this angle will also be alpha, right, because it is coming back to the same height. So if you think about it, if it comes back to the same height, okay, so I'll just give a quick explanation for this. So it comes back to the same height. The potential, if we consider, if you have some initial knowledge of conservation of energy, which is kinetic energy plus potential energy in this case, so the potential energy is the same for points A, or the source point A and the destination point B. So the kinetic energy should be conserved, which means the initial velocity should be equal to the final velocity, right? Also, so if this magnitude is v naught, this magnitude will also be v naught. And secondly, why are the angles same? So in the horizontal direction, the component of velocity won't change over time because there is no horizontal acceleration. So if so the horizontal component over here is uh, v naught cos alpha, right? Okay. And let's say this was some angle beta. Okay, so it will be v naught cos beta. So obviously alpha is equal to beta. This is just a quick explanation for why this is happening, and this is very crucial for, let's say, getting the time of motion, the horizontal range, these things. It's crucial. So now it's very simple. Now what we can do is uh, we can basically solve for the vertical direction, okay, to in order to get the time. So if we consider the vertical direction, we can say that uh, in the y direction, vy equal to the equation of motion, basically, right? Ayt, right? Now uy is equal to what? V naught sine alpha. It's in the positive direction, right? Let's write it here. V naught sine alpha. Okay, so uy is V naught sine alpha. Vy is, so it has a component in the downward direction, magnitude V naught sine alpha. So it's basically minus V naught sine alpha because it is in the opposite direction to that of the positive y-axis. And acceleration, so acceleration is again downwards with a value of basically the acceleration due to gravity g. So ay is minus g, right? So I'm representing it by ay. It's according to you whether you want to represent it by ay or wy, as per whatever is convenient to you. So now we substitute these values in this equation. So vy is minus v naught sine alpha, uy is v naught sine alpha, plus ay is minus g times t. Okay, so t over here is basically the time of motion, right? Capital T, the thing which we want to calculate. So this means we'll bring gt onto the left, we'll bring v naught sine alpha to the right, it becomes 2 v naught sine alpha, right? So this becomes, so the time of motion t becomes 2 v naught sine alpha by g. So this is a very important formula which will be required many a times while solving questions. Yeah, so basically this was your A part. Okay, this is done. B part is maximum height of ascent and the horizontal range, and of course this what value of alpha will they be equal to each other, that we can find after finding out the heights and the horizontal range in terms of basically v naught, alpha and g. Okay, so let's first of all go for what's the term, maximum height of ascent, right? So basically at maximum height of ascent, okay, again we'll solve it in the y direction, right? So in the maximum height of ascent, so again let's consider this, like you have your uy equal to v naught sine alpha as usual, as in the first case. Basically in this case your vy becomes what, that at the maximum height of ascent, basically when would there be a maximum height? Think about it. When the body is not going any further in the upward direction, right? So basically when its upward velocity is 0, right? So you can also think about it in this way, that maximum height, so for anything maximum, the derivative of it, dy by dt, at that instant t naught, where the particle has the maximum height of ascent, that should be 0, right? This means Vy at that t naught at that instant basically should be 0. So this is the thing at the maximum height of ascent. So Vy is equal to 0. Fine. And let's say we represent the maximum height of ascent by capital H. Okay. So now you know from other equation of motion or kinematics that Vy square minus Uy square equal to 2Ay into, I would say, let's say I'll represent it by Sy, displacement in the y direction. Okay. Vy, Sy is obviously capital H, because so I'm basically representing this by capital H. Okay. So that's basically the displacement, and it's in the positive y direction, so Sy equal to H. So Vy square is 0, Uy square is V naught square sine square alpha 2. Ay is, so again from the first part it is minus G, Sy is capital H, which we want to find out. So this means H is equal to V naught square sine square alpha, just write it neatly, sine square alpha by 2G. That is your maximum height of ascent. Okay. Now what we need to find is the horizontal range, right? So the horizontal range will be represented by, or denoted by, basically AB is represented by, say, I don't know, let's represent it as, if we don't want to represent it by R because might be confused with the curvature radio of trajectory, let's represent it by capital X, right? No confusion. So you want to find capital X, right? So how would we find capital X? So one simple way to find capital X is, so if you think about it, so in the X direction there is no acceleration, right? So in the X direction, basically Ax is equal to 0, right? Displacement is equal to velocity into time, so uniform velocity. So displacement x is equal to basically velocity in x direction. I can write it as Vx because it's a constant, right? Into time taken, right? Into time taken is what? Capital T, which we have found in the A part. So Vx is nothing but V naught cos alpha into capital T, 2 V naught sin alpha by G. So this basically gives me V naught square times 2 sin alpha cos alpha by G, right? Now 2 sin alpha cos alpha is nothing but sin 2 alpha. So this becomes V naught square times sine of 2 alpha divided by G. Okay. So that's the thing. Now the sub part of part B is, to what value of angle alpha will they will be equal to each other. So for the next sub part where we need to find out alpha for which h is equal to x. So h sine square alpha by 2g, just a second, v naught square sine square alpha by 2g, sorry, and capital X is v naught square sine 2 alpha by g. I'll just expand it. V naught square into 2 sine alpha cos alpha divided by g. Right? Okay. So, right. So your g and g cancels out. V naught square and v naught square cancel out. Sine alpha and sine alpha cancel out. Okay. So basically this becomes tan alpha is equal to 4. Right? So alpha is basically tan inverse 4. Basically this is the angle at which the horizontal range equals the maximum height of ascent. Cool. So after B part, let's go to the C part. The equation of trajectory y of x, where y and x are displacements of the body along the vertical and the horizontal respectively. Okay, so till now we were just considering like just the parts where like where the particle has the maximum height or when the particle returns to the ground, but this now we need to find out a general equation of the trajectory. So one way to go about it is find out y in terms of t, find out x in terms of t, and then solve using the two equations, write y in terms of x, right? So let's go in that fashion. So finding out x is very simple. So x of t, because as we have already mentioned in the x direction, the magnitude of the velocity remains the same because of zero acceleration in the x direction. So this is nothing but vx times t, and as you know vx is v naught cos alpha times t. Okay, so this is equation 1. Let's now let's go for y of t. Okay, so now for y of t there is an acceleration, right? So you can use the ut plus half at square. So basically uy t plus half a y t square, and now we have already used uy in previous parts. So uy is nothing but v naught sine alpha times t plus half ay is minus g times t square, right? This is equation 2. This is y of t. Now from equation 1 we get time t as, I'll just replace x of t by x because we are replacing time by basically we are eliminating the variable time in our equation. So for the timing I'll just write it as x by v naught cos alpha, right? So this, let's say this is 3, substituting 3 in 2, what do we get? Again I will remove y as a function of t. I will just write y is equal to v naught sine alpha into x by v naught cos alpha minus g by 2 times t square, which is x square by v naught square cos square alpha, right? So v naught cancels out, so we have got y is equal to x times tan alpha minus gx square, just a second, is gt square by 2 minus x minus g by 2 t square is x square by v naught square, okay, square alpha square by v naught square cos square alpha minus g by 2, yeah, okay. So my, sorry, I was just checking if it is if the calculations were correct. So comes minus gx square by 2 times v naught square cos square alpha. So this is your projectile equation, y in terms of x. So basically this is also done. Okay, so what's the next part now? Okay, the curvature radii of trajectory at its initial point and at its peak. So for this we need to know, like, there is an equation of the curvature, radius of curvature, for so basically given a trajectory y of x, we can find out the radius of curvature. Just give me a minute. So radius of curvature is, I am representing it by r. So this is basically at any general point. Okay, this is really important. And so it is 1 plus dy by dx whole square whole power 3 by 2, right, divided by mod of d2y by dx square. Sorry, yes. So this is the thing. It is really crucial formula, so I suggest that you memorize it for now. So you need to find out at its initial point and at its peak. So by peak it basically means this point, which is the point at which it has the maximum height of ascent. Okay, so at first of all at the initial point. Okay, let's do one thing. We already know what is y in terms of x. Let's just directly differentiate it in terms of x. So it's very simple. So just write it here. Dy by dx, any general point, is tan alpha. So x square when differentiated becomes 2x, 2 and 2 will cancel, so minus gx by v naught square cos square alpha, and d2y by dx square, tan alpha is a constant, and again you're differentiating with respect to x, so basically d2y by dx square is a constant, which is minus g by v naught square cos square alpha, right? And if you do a mod over that, this minus sign becomes a plus, right? Okay, so there you have it. So at the initial point x is equal to 0, as you already know, right? So it very simply becomes, so capital R, what would it be? So basically your dy by dx, first of all, what would it be? Dy by dx at x equal to 0 is tan alpha, right? Right. Okay. So your capital R becomes 1 plus tan square alpha whole power 3 by 2. Actually, there was another simpler way to basically find out dy by dx at the initial point. Since it is being thrown at a, so basically alpha is the angle which the velocity makes, right? So basically it's like the tangent, I mean, so the dy by dx at that point will be the tangent of the angle at which it makes with the horizontal. Is the velocity it makes with the horizontal, which is alpha. That is why it is tan alpha. So that also we could have inferred, but it's fine. This way is also fine. So 1 plus tan square alpha whole part 3 by 2 divided by mod of d2y by dx square, which is a constant, which is g divided by v naught square cos square alpha. Okay. So secant square theta minus tan square theta equal to 1. So 1 plus tan square theta is secant square theta. So this becomes secant square whole part 3 by 2 becomes secant cube alpha, right? And v naught square cos square alpha come in the numerator, right? Divided by g. Cos square alpha will cut secant square alpha, right? So we'll be just left with a secant alpha, right? So we can also write it as v naught square by g cos alpha. So this is basically your radius of curvature at the initial point. Now if we want to find at the peak, right? So at the peak, dy by dx is similar logic. The velocity makes an angle of 0 in the x-axis. So dy by dx is 0, right? So basically your capital R is nothing but dy by dx is 0, so 1 by mod of d2y by dx square. So 1 by g by v naught square cos square alpha. So this becomes v naught square cos square alpha divided by g. Yes, so basically you get the two radius of curvature values. So yeah, so this is a very crucial problem in the sense that if you I would suggest that you remember some of these values because it would help in the later problems. So the time of motion, so basically the time of motion is twice the vertical component of velocity by g, right? The whole basically time of motion, the maximum height of ascent is square of the vertical component by 2 times g, right? This is important. The horizontal range is v naught square sine 2 alpha by g. Okay, this is, you can infer it easily. Yeah, this equation is sort of important. Y is equal to x tan alpha minus gx square by 2 v naught square cos square alpha. And the radius of curvature, of course, if you like sort of know this formula, then it's very simple to get. But yeah, it's always preferable to remember the radius of curvature formula, right? So this is how it is. This is the formula. So it's better to remember. So this problem was sort of crucial in terms of the formulae which were sort of used and were sort of derived. So yeah, it was a crucial problem from that perspective. So yeah, I guess that's that. And Again, this problem would serve as a template for the problems that you will basically come after this, the projectile related problems. uh, so yeah, that's it. Thank you.